My name is Matthew Hall, and this is Lab 5, Magnetic Braking with Faraday. And so the purpose of this experiment was to determine the amount of time that it takes for the magnet to fall down a conductive tube of aluminum foil. And what this does is relates the downward force already that's being brought on to the bar magnet by gravity, and it relates that to the magnetic force that opposes that gravity going in the upward direction. And so to compare the amount of time, we're going to take time trials in an experiment and relate that to a computational model in GlowScript, which uses formulas such as Faraday's law and the Biot-Savart law and Newton's laws, which are some of our main principles, in order to find the precise amount of time it will take to fall down a specified length of tube. And on the bottom of the page, we see multiple of the equations that we'll be using. So in this lab, we're going to use a couple of materials, including a timer, a bar magnet from Lab 3, an aluminum tube, and a ruler. And so the procedure of this lab is we're simply just going to drop a bar magnet down a tube of conducting material, and we're going to record the amount of time that it spends inside of that tube. And so a couple of dimensions that we found of this tube: the length is 0.33 meters, the width is 0.007 meters, the inner radius is 0.021 meters, the magnetic dipole moment using the bar magnet from Lab 3 is 3.84, and the mass of this magnet is 0.025 kilograms. And so through our experiment, we found 5 times, and the average ended up being about 1.5 seconds. And this will be used to compare against our computational model. So a couple of the screenshots we see here make up the GlowScript code, and we used values such as the dimensions of the tube, the mass in the magnetic dipole of the bar magnet, and the two bottom ones are how we integrated Faraday's law, Newton's laws, and the Biot-Savart law into the GlowScript code. And so altogether, we see on the right that the amount of time in the tube was approximately 1.786 seconds. And we could see the graph that relates velocity and time, and we see that velocity increases, the magnitude of the velocity increases very suddenly, but then throughout the majority of the time it spends falling, it reaches its terminal velocity, because the magnetic force is opposing the force of gravity. So it's not accelerating, it's falling with a constant speed. And so some of the final questions we see here is, what if the resistivity of the conductor were reduced as close as possible to 0, and how would this change the falling magnet's speed and the time? So according to Ohm's law, we know that a decreased resistivity leads to an increase in current. So essentially, if the resistivity was reduced to 0, we would see a very large current, which will increase the magnetic force going upward and increase the time of the fall. Additionally, we ask, if there are holes and slots cut into the tube, how will this affect anything? So the presence of holes will induce the idea that there are less rings throughout the tube. And less rings is directly related to the Biot-Savart law, where we now have a decreased amount of current, decreased magnetic force, and this will decrease the time of the fall.